second module and addresses learning objective number 2. Describe the statistical principles that govern interpretation of genetic population data. The module learning objectives are: describe the binomial, multinomial, and normal distributions, and describe the laws of probability and the product rule. I will take you through the material using slides and also some video clips from a workshop presented for NFSTC by Dr. Greg LaBerge, Director of the Denver Police Department Crime Laboratory. Let's begin by taking a look at distributions, starting with the binomial distribution. The binomial distribution describes the probability distribution arising from n independent trials, where each trial can have one of two outcomes. Tossing a coin is an example. If we toss a coin n times, and every toss has the same chance p of coming down as heads, then the probability of obtaining x heads in a row is p times p times p, etc., which equals p to the power of x. And the probability of n minus x tails in a row is 1 minus p times 1 minus p times 1 minus p, etc., which equals 1 minus p to the power of n minus x. What about some other sequence of events rather than x heads in a row? We can calculate the number of ways of ordering x heads and n minus x tails in n outcomes. It is n factorial divided by x factorial times n minus x factorial. N factorial is 1 times 2 times 3, etc. We can use the binomial distribution to calculate the probability of a specified event. If we denote the probability of x successes, where a single event has the probability p of occurring, as the probability of x given p, then the probability of x successes is n factorial divided by x factorial times n minus x, all times p to the power of x, times 1 minus p to the power of n minus x. Let's illustrate this with an example. We have a bowl containing blue and white marbles. 25% of them are blue. If we sample with replacement 10 times, what is the probability of drawing 6 blue ones? Applying the above equation for the probability of x given p, x is 6 and p equals 0.25. 10 factorial is 3,628,800. 6 factorial is 720. P to the power of 6 is 0.000244, and 1 minus p to the power of 10 is 0.316. Therefore, the probability of drawing 6 blue marbles in 10 tries is 0.00162. So what is the relevance of this to us? We wish to make inferences about allelic proportions based on database samples that are much smaller than the populations that they represent. We are trying to estimate one or more parameters of the population from the observed composition of our sample. A single locus, two allele situation is described by the binomial distribution. But what if we have multiple categories? The basic approach of the binomial distribution can be extended to a multinomial one. For m categories, the probability of x successes in each category is given by n factorial divided by x sub 1 factorial times x sub 2 factorial, and so on, up to x sub m factorial, all times p sub 1 to the power of x sub 1 times p sub 2 to the power of x sub 2, and so on up to p sub m to the power of x sub m. This is a daunting equation, but when dealing with allele distributions, we can consider one allele at a time, and the binomial distribution can be used. We can describe any probability distribution by measuring the frequency of occurrence of individual events in a representative sample, and plotting the results in a curve, where the x-axis is the value and the y-axis is the frequency. The equation that describes the curve incorporates parameters mean and variance, which contain information about the magnitude of the event values and their spread. The mean, or mu, of a binomial distribution of n trials of an event with a probability of p is given by n times p, and the variance, sigma squared, is given by n times p times 1 minus p. We are probably more familiar with the normal distribution used to describe continuous random variables. The plot of values against frequency gives a symmetrical bell-shaped curve. The curve is defined by the parameters mean and variance. The spread of values, or the width of the curve, is a function of the population variance, and its height is a function of the mean. For a sample, the mean is given by the sum of all the individual values divided by the number of values. The variance is given by the sum of the squares of the deviations of each individual value from the mean. We can estimate the population mean, usually denoted as mu, and variance, usually denoted as sigma squared, by using degrees of freedom, or n-1 in this case, as the denominator rather than n. The standard deviation, the square root of the variance, can be used to quantify the spread of results. A small standard deviation indicates that the data points are clustered closely around the mean, and a large standard deviation indicates that they have a much wider spread around the mean. Approximately 68% of the values will lie within the range of the mean, plus or minus 1 standard deviation. 95% will lie within the mean, plus or minus 2 standard deviations, and 99.7% will lie within the mean, plus or minus 3 standard deviations. If we have a large enough sample, or several separate samples, the central limit theorem says that their distributions will tend to the normal distribution. This is useful because the normal distribution can be used to calculate confidence intervals. This is used to address the sampling variability when we calculate allelic frequencies from database samples. The probability of an allele frequency is the same as its proportion of the sample. That is x divided by n. The theory behind confidence intervals is complex, but the formula for a 95% confidence interval is shown in the slide, illustrating the relationship between the confidence interval and the normal distribution parameters. The correct use of a confidence interval estimate in regard to allele frequencies is to say that the spread of the values covered by the confidence interval will include the correct population value 95% of the time. Be careful not to confuse this with the concept of the probability of the proportion lying in the interval. Finally, the interval is a distribution about a central value. We use the one-sided interval for allele frequency data as we wish to take the conservative approach that gives a more common allele frequency. Here is a video of Dr. Greg LaBerge discussing confidence intervals.
What is estimation? Well, there's no way you can sample the entire population. The only thing you can do is get a sample of it. From that sample, hopefully the sample's large enough because we've decided what our outcome is going to be, we can generate an estimate of how much power or how much sample size we're going to need to detect that difference. Go out and sample it, generate parameters from that. What's a parameter?
Guideline or a rule?
A parameter of a model.
So
Parameter.
what alpha rate you're willing to accept?
That's one of them. The mean, standard error, those are parameters that come and play a role in defining the model. Okay. And then an estimation, once you get the model, if it's right, which is a big if sometimes, but large enough sample size, do you guys remember the central limit theorem from statistics? Central limit theorem. What is that? Basically, the central limit theorem says no matter what you start with, if you get a large enough sample size with repeated sampling, you're going to get a normal distribution. Ultimately, everything will collapse to a normal bell-shaped curve with enough sample. Your sample may not be large enough to do that. So you might have to use an alternate distribution like a chi-square distribution or like an F distribution or a Pareto distribution. There are many different types of distributions, a T distribution. Ultimately, with enough sample size in the correct model, they will converge to being a normal. The normal allows you to make generalizations about the larger population, right? The larger population, for more or less, is going to be normal. So if your sample has the same distribution as the population, your sample is a good sample and allows you to make estimation on that population now. Hence the crystal ball kind of feeling. Statistics allows you to get a feeling for what the general population would have.
We have used the term probability without definition up to now. Probability is a description of a likely occurrence of a particular event, usually expressed on a scale of 0, the event will not occur, to 1, the event is certain. Probability is often illustrated with reference to a pack of cards. What is the probability of being dealt a king? There are 4 kings and a 52-card deck, so the probability is 4 in 52, or 0.077. The probability that we are interested in is what is the probability that the suspect left the bloodstain. We can use the shorthand way to describe the probability of an event, probability A. This means the probability of event A. We can tighten this up by writing the probability of A given E, which is the probability that A is true given the evidence E. There are some laws of probability that we must know, and as discussed above, the first law is the probability that an event lies between 0 and 1. We can illustrate this with reference to throwing a die. For the event, the die will show an even face, 2, 4, or 6. What is the probability of A given E? E equals 6, therefore the probability of A given E equals 3 divided by 6, or 0.5. It follows that if the probability of an event A is P, the probability of the event not A is 1 minus P, provided that the events are mutually exclusive. This is the second law of probability. Therefore, the probability that event A is not true is written as the probability of not A given the evidence, or 1 minus the probability of A given the evidence. Again, we use the die to illustrate this concept. If A is the event that the die shows an even face, and B is the event that the die shows a 1, the probability of A is 3 divided by 6, and the probability of B is 1 divided by 6. Therefore, the probability of a throw resulting in event A or event B is 3 divided by 6 plus 1 divided by 6, which equals 0.67. What if the events are not mutually exclusive and the outcome of event A does not influence the outcome of event B? This is covered by the third law of probability, which states that the probability of non-mutually exclusive events occurring is given by the product of the probability of each event occurring. We can write this as the probability of A and B, which equals the probability of A times the probability of B. Returning to the die example, if event A is that the die shows an even face, and event B is that the die shows a 1, and we throw the die twice, the probability of A and B equals 3 divided by 6 times 1 divided by 6, which equals 1 divided by 12, or 0.83. Finally, we can consider the law of total probability. If events A and B are mutually exclusive and exhaustive, that means B equals not A, then for any other event C, the probability of event C is the probability of C given A times the probability of A plus the probability of C given B times the probability of B. Going back to the die one more time, you roll a fair die. If you roll a 1 or a 2, you flip a fair coin. What is the probability of getting no heads? The outcome of no heads depends on something we don't know, the outcome of the roll of the die. Let event A equal rolling a 1 or a 2, so the probability of A equals 2 divided by 6. Let event B be the rolling of a 3, 4, 5, or 6, so the probability of B equals 4 divided by 6, or 1 minus the probability of A. Let event C equal no heads for the coin toss, which equals 1 divided by 2. The probability of C is therefore the probability of C given A times the probability of A, plus the probability of C given B times the probability of B, or 1 divided by 2 times 1 divided by 3 plus 1 divided by 4 times 2 divided by 3, which equals 1 divided by 3, or 0.33. We have mentioned mutually exclusive events a few times. We also need to consider independence. Events A and B are independent if knowledge of one does not affect the probability of the other. The probability of A given B equals the probability of A, and the probability of B given A equals the probability of B. Therefore, for independent events, the probability of A and B both occurring is the probability of A times the probability of B. This is the product rule. In everyday conversation, people sometimes use the term odds as meaning probability. They are not the same. The odds of an event is the ratio of the probability of the event to that of an alternate event. So, the odds of an event A is the probability of A divided by 1 minus the probability of A. For example, what are the odds that two dice will both show an even number when rolled? The probability that both will show an even number is 0.5 times 0.5, or 0.25. Therefore, the odds that both are even is 0.25 divided by 1 minus 0.25, or 0.25 divided by 0.75, which is 0.33. That completes this module. The next and final will deal with the interpretation of DNA results. To test your understanding of the statistics module, please work through these review questions. Number 1, we have a fridge containing 12 blood transfusion packs. 6 of them are type O, and the rest are type A. If we pull out a pack, take a sample, and replace the pack, and repeat this 5 times, what is the probability of drawing 2 type O packs in the 6 draws? Question 2. Define the parameter and name the parameter that describes the spread of the values in a frequency distribution. Number 3. Which of these is the correct use of the confidence interval? A. The spread of values covered by the confidence interval will include the correct population value 95% of the time. Or B. There is a 95% probability that the population mean is included in the calculated confidence interval. Number 4. What are the odds that the first 2 packs drawn from the fridge in the situation described in question 1 are both type O? Number 5. Define the second law of probability. And number 6. Define the product rule and describe the conditions that must be met for it to be valid.